quantum mathematics at Dansk University in Denmark. He also works in UC Berkeley in the US. He's an expert in symplectic geometry, algebraic geometry, node theory, and mathematical physics. And he's going to talk about categorification of quantum groups via Fukaya categories. Let's welcome.
Thanks. It's a pleasure to be here. First, let me give some kind of history and motivation. So this will not be a kind of such systematic history, but so if you're familiar with knot theory at all, you will know that there's something called the Jones polynomial. You can define it in various ways. There's maybe the original way is you define it as a trace of a braid group action, braid group representation. And so, I mean, you present your knot as the closure of a braid, and you define some action of the braid group on some vector space. But to produce this action of the braid group on some vector space, there are various methods. One was maybe the original. One was just to directly define. There's many ways. And one is to just define a map from the braid group to the Hecke algebra, and then use some knowledge about representation theory of the Hecke algebra. Another way is, maybe one way. Another way is to find a braid group action from monodromy. So kind of monodromy, KZ equations. And maybe another way is, another way has to do with braided monoidal categories. Braided monoidal categories. And specifically, you need to produce the braided monoidal category having to do with representations of quantum groups. So there were many interesting lectures yesterday about quantum groups. And I emphasize, the reason I've mentioned these three methods is that the different approaches to categorifications in the literature pursue different different generalizations along these lines. And maybe I'll add a zero, which is historically maybe after these, but from some point of view, simpler, which is just, you can try and define such a thing by resolve all crossings of the knot by some skein relation, So what 0, 1, 2, and 3 all have in common is they give you some procedure for computing some number which depends on some amount of choices, and then a posteriori you have to check that it didn't depend on your choices. Okay, so then there's maybe kind of the fourth way, the fourth understanding of this business, which is this this kind of a piece of some topological field theory, and this is this kind of Witten-Reshetikhin-Turaev business. Invariance. So some story about this. So this some kind of, maybe I could have called this part some kind of prehistory. And afterwards, people got involved in this business of categorification. This is some kind of story, not so recent anymore. And what it's about is, whereas before we had things like numbers, and the Jones polynomial is some kind of number or polynomial or whatever, and you promote those to vector spaces where this map is take dimension or something. And meanwhile, sometimes there are vector spaces. And this is kind of vector space, which arises at the state space of this topological field theory. And you promote these to categories, which is why it's called categorification. Maybe just to mention about which of these, so the reason I wrote these on the board is to say about this kind of which of these things have been categorified and how and when. Okay, so Kavanov's original approach to categorifying the Jones polynomial more or less categorifies this. So this Kavanov. Maybe I'll put categorification yellow. This is Kavanov. Categorify this. And then I think later maybe he categorified this also. Some piece of this story is some piece of this story here is categorified by Ben Webster. So I'll explain maybe later which piece he did and did not categorify. And then maybe today, but what I'll discuss today, it's about somehow these two things. And this, no one knows how to do. Okay, that's the situation with categorification. So that's one kind of general business. And maybe I want to explain. So, there's many. Where are you going to get a category from? Sources of categories. Okay, so one possibility is you can just write one down. So one option is just write one down. And by write one down, I mean maybe you write like generators and relations for a category. This is a thing you can do, people do it. So generators and relations. The advantage of such a thing is that then it's explicit, you can see what it is. The disadvantage is maybe you have no idea what it means. Another common approach is, or maybe some specific way people do this first thing is you first write down an algebra. You can just take modules over some algebra. So you have to figure out what algebra. And another thing people do is they take maybe coherent sheaves over some algebraic variety. That's kind of just another version of the previous example. Variety. But there's a fourth possibility, which is what, or maybe they take D modules or something, D modules. There's a fourth possibility, which is what we do today, which is you can take what's called the Fukaya category of a symplectic manifold. And of these various options, maybe it's the most complicated. And so you would ask, why would you ever pursue this way of producing a category instead of the others? And one answer, I'm going to give you two answers. And one answer is, for this business, we want not just a category, but eventually a category with a braid group action. Okay, so you can ask, like, what are sources in mathematics of a braid group action? So eventually on categories, but first we can ask on vector spaces. And there's basically two kinds of sources. One is, again, you can just write one down. And what write one down means is the braid group, it has some well-known generators and relations. So you say what the generators do, and you check that it respects the relations. So that's one approach to producing a braid group action. I think the only other approach I know is you can take monodromy of some kind of differential equation, or maybe defined on For the braid group, you want on the configuration space of points in the plane. So monodromy of some kind of connection on the configuration space of endpoints C. And so this makes sense for a vector space. Like a vector space, that's a way you can get a braid group action on a vector space. But you cannot use this to get a braid group action on categories in any of these three approaches. Or at least to the extent that you could, you would have to already know the braid group action to build this connection. However, what is a feature of this kind of feature of symplectic geometry is that it's locally constant in families. So if you have a family of symplectic manifolds over this kind of configuration points of configuration space of endpoints in C, there is a monodromy action on the Fukaya category. Okay, so that's so this one reason why this is a good idea is that this you can use this and produce braid group actions on categories. And not just braid group actions. In general, if you want the action of some kind of group, if you find some family of symplectic manifolds defined over some space, which the fundamental group of that space is your desired group, you can produce a group action on categories. And you know, in the old days, people had to like work a lot to prove various coherences and so on, but you get all of those for free when you produce things this way. Okay, so that's one maybe motivation for using this kind of Fukaya category. And another motivation is that I'll just say this one out loud because we had this talk yesterday of Lustig who reminded us all about canonical bases and so on. And so you can ask, from the point of view of categories, why should there be canonical basis in the decategorification? And from point of view of Fukaya category, the answer is that morphism spaces in the Fukaya category, they come with a God-given basis, namely intersection points of Lagrangians. And so this is related to some questions about this kind of canonical basis. Okay. That's related in a slightly complicated way. A less complicated way is that the smooth Lagrangians themselves are going to give you the canonical basis on the decategorification. All right. So then maybe just one more piece of motivation has to do with this question mark. So if we want this Kavanagh homology to be some, to extend up to some TFT, we should imagine, like, where does topological field theories come from? They come from gauge theories in physics. And so we should imagine that the Kavanagh homology is some part of some gauge theory. And you're going to ask, what gauge theory? And so let me just remind you of how in the history of mathematics, in some recent history of mathematics, various gauge theories, so there's kind of a general procedure, which is we have a 4D gauge theory. 4D gauge theory. You can do what's called reducing on a, you can reduce on a surface, so reduce along surface. In other words, you hold the fields kind of mostly constant in one direction, and then you get an interpretation of this gauge theory as maps from said surface into a moduli space having to do with vacua and the remaining dimensions. On the reduced theory. Okay, and this has been very important in mathematics, in particular, the kind of Seiberg-Witten theory, which is very influential in four-dimensional topology. Reduces to what's called, what is now called this kind of Heegard-Floer theory. So this thing is something about gauge theory on a Floer manifold. This is something about Lagrangian Floer theory in symmetric power of a surface, and what this symmetric power comes because it's the appropriate moduli of vacua. There's some story, so people, it might have been natural to think that this Donaldson theory would reduce to something related to Kavanagh homology, because this guy has some input, which is the gauge group, And so you might have thought that maybe you would get Kavanagh homology here, but you do not. So you get something which is not quite Kavanagh homology. And this is work of Kronheimer and Ravka. You get something which has some spectral sequence to Kavanagh homology or Kavanagh homology or something. Kronheimer, Ravka. And this, of course, is the work of Ojratzawa. I guess Ojratzawa, they didn't prove this arrow. Other people later proved this arrow, but they somehow, inspired by this arrow, defined the Hegardt-Floer theory. And Witten has recently explained this thing called the Haydes-Witten equations. And this is something which lives actually in 5 dimensions. And this is something that Witten conjectured has to do with Kavanagh homology. And what I'm going to talk about today, so there's a reduction of this due to Gato and Witten. And the result should be maps of a surface, some theory of maps of a surface to some sort of moduli of some 3-dimensional theory. And that's what I'll talk about today. Okay, so this it's something which bears the same relation to this theory as the Hegardt-Floer theory bears to the Seiberg-Witten theory. Fine. So now, after that, I begin to get to the point. Oh yes, I had this one also. Okay, so now I have to recall for you something else, which is the work. I have to remind you what is this kind of what's called Coulomb branch of a quiver gauge theory. And this it's something from physics, but it was brought into mathematics by the work of Braverman, Finkelberg, and Nakajima. And what it is if you have a group, if G is a group, and it has some representation V, then from this data you produce something, which I'll say like 3 words about how you produce it, but you produce something associated to the group and this representation, or really to its to the representation times its dual. And the way you produce this thing is you take the spectrum of a certain algebra, and that algebra is the K. I'm going to use K theory. There's also a version for homology. Is the K theory of the moduli of bundles, a G bundles with along with a section of the V corresponding V representation on some kind of screwy space, which is the disk with a doubled origin. Okay, so in other words, it's two bundles on the disk together with an identification away from the origin. People in geometric representation theory mess around with this stuff all the time. And this becomes an algebra not with the product on K theory, so let me put that there, but with some kind of convolution product. And this convolution product has to do with the fact that you can put the disk with the double origin inside the disk with the tripled origin in 3 different ways. So using that fact, you like include along 2 of those ways, tensor, pull back along the 3rd, you get some convolution product. These guys prove that it's not obvious at all that that convolution product is commutative, and then they take the spectrum of that thing, and that's the space. Okay, so that's what it is. And so you can ask, how on earth would you ever get your hands on this kind of space? Because people have, these guys and other people have done a lot of work about this. But the first thing that you learn about it is it has a map to the kind of the torus of G mod the Weil group of G, and the fibers. So the fibers are kind of mostly just another copy of G. Okay, so it's like it's approximately G times G mod W, but away from some high codimension locus. T, sorry, T. Yeah, the other thing I said was correct. It's like G times G mod W, but G times G mod W. Or whatever, this is correct. Yeah, thanks. Yeah, I'll say something better in a second. Yeah, okay, great. So that's one recollection I have to make. And the other recollection I have, so here's what kind of other recollection, which is about what are called Kavanagh, Lauda, Ruquier, Webster algebras. And what is this? First of all, what are they for? There's something that these guys introduced in order to categorify the quantum groups and their representations. So these first three people introduced some version that's good for categorifying quantum groups. And this guy, he introduced some variant, which can also use to categorify the representations and their tensor products. And so let me just say what those things are. So okay, so maybe definition. The input to this definition is, so given a graph, a gamma, this graph will eventually be a Dinkin diagram, and a collection of red points. I call them red because I'm going to draw them in red. On a line or a circle. There's a category. There's a category. Whose objects are, I'll just kind of say it maybe slightly informally. The objects of this category, so I said we fix some red points on a line or a circle. Here's some red points. And these red points, they're kind of labeled, red points, labeled by the vertices of the graph. So there's some red points, also some white points. So the objects are pictures involving red points and white points. So this is an object. And they should be labeled by the, maybe I'll just, in general, it's like this, but I'm going to, in the talk mostly, so in the paper we do any ADE Dinkin diagram. In the talk, I'm going to stick to SL2, so there's only one vertex to label it by. So in the talk, I'm always going to take this graph. Okay. So objects look like this, and then morphisms. 1, 2, 3, 4. They don't have to go from the same object to itself. Morphisms are pictures which look like this. The red lines, these objects are configurations of red and white points. And the morphisms are diagrams which look like this. So the it's got some kind of there's some kind of strands. These strands should go straight downwards. In other words, there's no like they always go down. They don't like go back up. Okay. So there's no horizontal tangencies of the strands. Maybe it's good to ask that they're kind of in generic position. So this is a morphism. Morphisms. Composition is stacking the diagrams on top of each other. So composition, you stack diagrams. And the morphisms are these diagrams, maybe modulo some relations. And I'll draw you now the relations. So the relations somehow the most interesting part, and I'll draw them. So So it's defined over kind of polynomials in two variables, which I call u and h bar. And I'm drawing the relations just in the SL2 case. Otherwise, there's more relations. Ah, yes, I forgot one thing. You can also put dots on the strands. There's one more relation, which is the, maybe I should have left more space for it. So, okay, so you can use these relations to kind of like rearrange these diagrams. All right, so that's the scalar W category. And I gave you a category, but I wrote algebra. The relevant algebra is you take the direct sum of all the kind of isotopic classes of objects and take its endomorphisms. So fine. So that's some category. So maybe if you wait for one theorem. Well, I mean, I can tell you these guys, what they prove is that, so what this version is some kind of version for Ben Webster, and he proved that if you take this kind of algebra I just said, and you take some certain quotient of it, then that categorifies certain weight space in certain tensor product of representations. Right? Yeah, so the basic result that we proved with this kind of proposed by Mina Aganagic and then proved with somehow many people is a theorem. So for gamma and ADE Lincoln diagram and A, a collection of points in C star with distinct arguments. There is a function. It's an explicit function, but I don't want to write it. There's a function depending on this A from this Coulomb branch. So okay, I have to say one thing in a second. This Coulomb branch. I'll explain this notation in 1 second. As such that this KLR W category for this kind of same data. So I said I should give you a graph and a collection of points on a line or a circle. I give you the arguments of those points. That's the collection of points. Embeds inside the Fukaya side L category of this space gamma B with respect to this function. Okay, and you expect it's an equivalence, but we didn't prove that. So I owe you the explanation of this notation, and what that is it's this construction for a certain G and a certain V, and so you take. I just should say that this when I write this M gamma B, it's what I previously called M G T star V, where D is a dimension vector for the quiver. So in other words, I put a number at each node, and G is the gauge group of the quiver. It's the product of GL EI, automorphisms, and this V is the representations of the quiver with that dimension vector. Is the direct sum of C DI Bj when there's a map from I to j. Okay, so with this G and this V, I apply this Coulomb branch construction, I get something. The claim is there's a function on that thing. You take Fukaya side L category. Fukaya side L category means that you take certain non-compact Lagrangians and you do something at infinity with them. Yeah, and this is the statement. What is frame? So that's true. The definition of this WA, the way we construct WA, in fact, involves this framing, but the space does not involve. I mean, space is for the unframed guy, but the definition of WA involves it. Yeah, I will say more about this. So I would like to. Is there a clock I can see somewhere? Okay, good. So yeah, now I will say some words about how to prove this theorem. Or at least, at the very least, how to construct the map and so on. Okay, so what does it mean to prove such a theorem? Well, you know, I gave you here a category by generators and relations, more or less. I said, what are objects? What are morphisms? What are relations of morphisms? So to prove this theorem, what I have to do is, well, I have to say objects go to objects, morphisms go to morphisms, relations, you know, composition goes to composition, etc. So I better, maybe I should say the 3 words about what is Fukaya category. Fukaya category is something you can associate to a symplectic manifold. Objects are Lagrangians, morphisms are intersection points between Lagrangians, and composition has to do with certain counts of holomorphic disks, which is a long story and the real structure of the thing. So for each of this kind of configuration of red and white dots on this line, I should give you a Lagrangian somewhere. And then for diagrams like this, I should give you intersection points of Lagrangians. And then this business about holomorphic disks, somehow, if you think what it means that when this is like a composition of 2 morphisms in this category, and this kind of statement says that there should be a certain holomorphic disk, kind of involving this intersection point. I mean, not the intersection point of these 2 lines, but the morphism between the Lagrangians I will provide you, which corresponds to this morphism, and this morphism. And similarly, all these relations, they say that there should be certain disks in some space. Okay, that's what one has to do to prove such a theorem. So, all right, let me at least say something about how we produce this Lagrangians. So, I mean, of course, we're going to have to somehow get our hands on this Coulomb branch in a way that's explicit enough to kind of be able to name things inside there. So that's the maybe half the work of this paper. I mean, that part of the work is mostly organizing other people's work. But let me anyway say what we prove. So theorem. So again, I'm going to state it. I'm going to state this theorem. I'll state this. Maybe I should say the names of who proved this theorem. So this theorem is due to Aganagic, Malenko, Yishuan Li, myself, and Peng Zhou. And of course, I should mention that Mina Aganagic has been proposing that something like this is true for many years now. So all right, so this theorem by this kind of same people, and I'm going to state it in the SL2 case here, but in the paper you'll find it in general. So the statement is that there exists a W equivariant isomorphism So I take this kind of tilde. So remember that this is this kind of m g t star v. It always maps to this t mod w, and I'm going to write m tilde for the lift up the w quotient. So the statement is that so this space it maps to c star to the d, and in this c star to the d, I'm going to delete the diagonal, the big diagonal, whenever 2 points collide, and I'm also going to delete the kind of I'm going to write this as HA, and HA means the union of hyperplanes when any coordinate is one of these points A. Okay, so I delete some locus in here. And I, up here, delete the preimage of this locus. And the statement is a W equivariant isomorphism, which sends this thing, maybe it's better to write the arrow this way. It kind of trivializes this vibration away from this locus. So this C star to the D, and I'm going to call this fact, so times this C star to the D minus the same stuff. So how to say it? Like this map is just the projection out the first factor, and I'm going to indicate these by y and u, because when I write u's, I mean these coordinates, and when I write y's, I mean these coordinates. Okay, just to distinguish them. So this kind of statement will not surprise anyone who has read this Braverman-Winkelberg-Nakajima, but this theorem goes on. So yeah, and this coordinate chart, it depends on the points on this coordinates A, on this choice A. So now this isomorphism has some properties, and the first one is that the sum of the ui, these kind of fiber coordinates, extends to a global function. So that's that function WA that I had written before and didn't tell you what it was. And this is one way to say what it is. But that's not, I mean, that's part of the point of the theorem. But maybe the main point is the following statement. And so if I have a map, so ultimately I'm interested in counting holomorphic curves in this M D. Okay, so now the point of this theorem is it's going to give me a way to do that. And so given a map, maybe I'll say something about, maybe before here, let's have some prelude. So I'm going to continue this theorem in just a second, but I'm going to give you some kind of slight remembrance. So this is something that people in Hegardt fluid theory use all the time, which is that a map to a symmetric power, if I have a map from a curve to a symmetric power, this is the same. And let me for now restrict attention to maps transverse to the diagonal. Transverse to the diagonal. This is the same as the data of d to 1 branch cover of this curve plus a map which I will call y to c star. Okay. And what is the correspondence? Well, this is giving d points of c star over every point in C, and this is giving d points in c star over every point in C. Okay, so that's the correspondence. Oh, and this transverse to delta is the same as asking this be kind of simply branched. So I want to describe maps. Now I want to describe maps from a curve to this M D And I'm going to describe that. So this space, remember, it maps down to this T mod W, which is C star to the D mod SD, or in other words, sim D C star. And so I want to describe maps like this. And to describe them, it's enough to say, like what is the data needed to lift a given map like this. Okay, so that's how I'll describe them. And so the statement is, under this coordinate choice, so given a map, at C to sim D C star transverse to, and now I'm going to ask it to be transverse not only to the diagonal, but also this kind of hyperplanes where any of the points in this sim D C star is one of the A's. So given such a point, the map so maybe given such a map, which corresponds to this map, given this map, this, as said there, it's the same data as this S, C, C star, and a map from, I'm going to erase this here now, and a map from S to, and here is why it's helpful. I call this C star Y, and here I'm going to call it a map from S minus delta minus HA to C star U. The map, the map extends. So if you think through about this equivariant isomorphism, a map from here to C star U is like saying I've given a map from the base curve C to this space, away from the preimage of this locus. Okay? And so the statement is that that map extends to C to this M star D at bullet D, if and only if the poles, we'll call this map U. The poles of U are simple. So U is a map to C star, so it has zeros, and you can discuss its zeros and poles on S. Its poles are simple, and they're all over. There's like one simple pole over each point of delta, and the zeros of U are simple, and they're over. So that's the theorem that tells you if you want to know how to find holomorphic disks inside this Coulomb branch space where we're going to study. It's enough to understand how to find holomorphic disks in a symmetric power, which we already understand in terms of this kind of this business. Plus some question about one more map from a curve to a curve with certain zeros and certain poles. And maps from curves to curves are not so difficult to think about. So that this is how this theorem. This theorem is the basic tool for all of this business. And let me say now how, at least to use this. So this theorem, it does like kind of three things. It lets you make Lagrangians. It lets you study their intersections, and it lets you count holomorphic disks. So in this discussion, when I translate it to this S, C sitting over H, a point in C sits over HA if the corresponding point of S sits over one of the points A inside this. maybe A is like many points, right? So, no, U is, yeah, so, sorry, U is just this map. U is, again, a map from C to the symmetric power is the same as a map from some cover of C to this, okay? So now, if I want a map from C not to the symmetric power but to the Coulomb branch, I have to give you another map from this S, and that map is called U. Maybe you're asking, you could have been asking, how does this sum of UI look, so to speak, from the point of view of S? And maybe that's this function. Okay, so now let me tell you about how to make Lagrangians, and that's very straightforward. So using this trivialization, I want to make a Lagrangian not inside here, but inside this thing mod Sn. And so to make a Lagrangian in this thing mod Sn, I should give you a Lagrangian in here on which, let's say, Sn acts freely and transitively. And then I can just descend it down the quotient. And the way I do that is the same way people in Hegardt-Floer theory do it. It's I give you kind of D Lagrangians in here and D Lagrangians in here, and then I take their products and let Sn act on that. And so the kind of Lagrangians, so this is supposed to be a picture of C star Y, and here is infinity and here is 0. And here's some kind of picture of C star U. I don't know why we draw this one like this and that one like that, but that's what we do for some reason. And an example of an object in this Fukaya category looks like maybe like this. Okay. And so this means I take like this Lagrangian times this Lagrangian and this, I mean, this times this, times this times this times this, times this, and then the symmetric group acts on all of it, and then that descends down into this thing without the tilde. So that's how you produce these Lagrangians. And this guy is what corresponds to like these 3 black points and these 3 red points. Okay, so this is the object to which I would send this guy. Okay, that's the nature of the function. Send this object to this times this. Now, so that's about objects. This cross or this one? Those are the points in A. And I didn't have to draw them here. Maybe I'll draw them in red. So this, these are the points. There's like A1, A2. The subscripts of the A mean nothing. They're just like 3 different points in this A. It doesn't have to be the same number. Yeah, maybe. A was maybe I did the wrong thing. I may have messed up the. I mean, yeah, there doesn't have to be D of the A's. There's any number of A's. Yeah, just any number of them. Possibly 0. That doesn't matter. The Lagrangians should not go through them. You can ask, where is the influence of this A felt? It's felt here. So this, I mean, it's felt here and it's felt here. So this trivialization, I didn't give you the formula for the trivialization. Whatever that formula is, it depends on the A. And it's set up to ensure these 2 properties. And those really depend on this point. Okay, so that's, maybe I'll say, just a few words about, just out loud, how to prove. I want to get to some other things, so I'll say maybe a few. How much time is it? Not so much. So yeah, the number of red dots is the number of A's. Okay. So yeah, maybe I won't discuss the rest of how to prove that main theorem, except to say, I'll just say maybe one word about it, which is that these Lagrangians, they all stay in the complement of this stuff. So the way we prove this theorem is that we first count disks kind of in this complement, or in other words, in this completely trivial space. And so here, it's straightforward to compute Fukaya category. And computing that, you just do it, and you find it corresponds to this stuff with u equals h bar equals 0. And then you have to figure out how to count disks through the remainder, and you count those disks weighted by the number of intersections with these guys, counted by h bar or u. And then so you count some disks. I won't discuss here how you actually count those disks. That's, of course, the real meaty part of the, I mean, there you have to actually do something. But let me mention now about this kind of, this braid group action, which is, so I was supposed to promise, I was supposed to produce you a braid group action at some point, and the braid group action has to do with just moving these A's around. So let me state another theorem. Theorem. This theorem we only proved for SL2, basically because of laziness. And this is with Elise Lepage, myself. And the theorem is that the braid group action, I mean, this functor, this kind of, this functor from before, from this paper, this ADSLZ paper, intertwines this kind of this monodromy braid group action with some something which Webster explicitly wrote down. Webster's action. So Webster wrote down in terms of this generator's relation some explicit braid group action. He proved it gives you Kavanagh homology, and we compute that that's what you get from the monodromy. So, hence can get Kavanagh homology. Okay, but now let me get to the. So this was maybe the first sentence. This what I've discussed so far is the first sentence in the abstract, and the abstract fortunately only had 2 sentences. And so let me say something now at the second sentence in the abstract. The monodromy. So I said this whole category, it depended on this choice of points A, and so you can move that. And this Fukaya category varies locally constantly as you do it, and so you get some monodromy action, and we computed it. So okay, so what has not appeared so far is anything about so this Webster, at least on the Fukaya side, we haven't discussed any quantum groups so far, and so I want to now remedy that. If you think about the nature of this description of this Coulomb branch, especially this explicit description, it's natural to ask, can you just replace this with some other surface? Replace with other surface. And the answer is yes, you can do it. So maybe I'll just say kind of like work in progress. And this is with Aganajek and Elise, and I don't know how you abbreviate someone, and myself and Peng Zhou. Basically, let me just, since for lack of time, let me say it kind of informally. So there's a similar story with C star replaced by another surface. And the key theorem about this, so these are surfaces with two kinds of boundary. So it's like a surface with kind of a dashed boundary and a dotted boundary. And so a dashed boundary and a solid boundary. And in such a surface, you can put these kind of red points if you want, but you also can not. And we allow this kind of curves to go to the solid boundary, but not the dashed boundary. So you can consider pictures like this. And the basic theorem about these is theorem. Maybe first, before the theorem, a remark. So a remark is that for the strip, this is now a strip. So here, this is a cylinder. I identified this and this, and now it's a strip. I don't identify them. And for the strip, when you do this, and you ask, so this guy, he's not just a category, he's a monoidal category. Because I can stick somehow two of them together. Okay, I can compose this way. And so the remark is that it's a monoidal category. And another part of the remark is this kind of same arguments tell you it's this Kovanov-Lauda-Ruquier categorification of the upper half of the quantum group. And then the kind of theorem about this stuff is that when you have some kind of surface, maybe some complicated surface, okay, and you cut it somewhere, so this is, and you cut it somewhere, then what you find is you have like two different surfaces now, which are both modules for this algebra. And the theorem is that the kind of category associated to a surface in this situation, so now I sum over all numbers of Lagrangians. Okay, so in this situation, let's call this whole surface, let's call this part A, and this part B, and kind of whole surface C. Now the category associated to C is the category associated to A, tensor over the category of the strip. So this is a theorem. The category associated to B. And the proof, I'll say one word about the proof of this theorem. The proof of this theorem is we construct what's called a sectorial decomposition with a symmetric power. And this tensor product is defined by some bar complex, which is a certain colimit. And the identification of that colimit of categories with this guy is a consequence of my old work with John and Shield. So that's one word about the proof of that. And the corollary of this thing is that this picture, I'll stop after this statement. This picture, so this thing, by this discussion, it's a trimodule for this algebra. And as a consequence of this theorem, this trimodule, it gives a coproduct, it gives, not a coproduct, it gives a monoidal structure on a certain subcategory of the representation category of the quantum group. And it's really the upper half of the quantum group. So this is this kind of long missing kind of categorical Hopf structure. All right, stop there.
Let's thank the speaker. Questions, comments?
So what is H bar?
That H bar?
Yeah, that H bar.
It's the counting. So as I was saying, over there it's just a formal variable. But in this Fukaya category business, it's the counting parameter for how many times your disk intersects. Hopefully I get this right. I believe it's the diagonal. So you remember in this theorem that used to be here, it said that if you delete the diagonal and delete some other divisor, then the Coulomb branch trivializes. And so, and the proof of this theorem, this main theorem with Mina and company, was that first you prove it at u equals h bar equals 0, which means you compute Fukaya category minus the symplectic manifold minus those divisors. And that calculation is basically trivial. You just do it. And then now you have to count with those divisors. And what does that mean? That means now holomorphic curves are allowed to pass through those divisors. And so every curve which appears, it comes with like how many times it intersects those divisors, and we count them by this u and this h bar. And the h bar, hopefully I get it right, is the one, yeah, so you can see here that, I mean, u is appearing when somehow the red stuff is involved. And so that's about when this a divisor is put back in. And the h bar is appearing when, so it's, I guess it's, so I didn't tell you what this dot was. What this dot was is, you remember there was this factor that looks like this, okay? And I put a point here for some reason. And the reason I put this point here is that the superpotential function I wrote was the sum of these ui. And that means that the way you wrap in this Fukaya category is you wrap on this side, but you're forbidden from wrapping here. And so this dot over there is how many, like, you know, if you wrap here, then you intersect yourself like a natural number many times, and you put one dot for each. Okay, so those are the morphisms, and each one is a dot. And so, commuting this dot with this other thing has to do with whether you do that wrapping before or after some other movement. But the description of this as the fiber was only correct away from that divisor. So when you put that divisor back in, there's some kind of correction, and that correction picks you up this.
Thanks. And also maybe another question. So when you replace it by other surfaces, do you mean you have a definition for the Coulomb branch, or
yeah? So okay, that's a long story. So but I'll say something. So for surfaces which have the to state this to get this corollary, I only need to do it for surfaces which can sit inside of a disk. Okay, and for such surfaces, I can just take appropriate subset of that C star. And so one can, you can kind of cheat your way out that way. What's expected is that it's a certain moduli on any surface, it's a certain moduli space of monopoles. But exactly which moduli space of monopoles, with like what boundary conditions and so on, is, yeah, we're trying to sort that out.
Thanks.
So using this kind of gluing procedure, can you get, for example, like genus 1 with one non-dashed boundary?
Yes.
Okay.
There always has to be some solid boundary.
Okay.
But
any genus with.
Well, okay. So this is related to this question. So we haven't written down. We haven't actually thought so hard about writing down the space. But suppose you've written down the space. Suppose you like knew which moduli space, monopoles, whatever it's supposed to be. Then the argument which proves this theorem applies. So it will compute the category associated to that space.
And sorry, but and then can one action of the mapping class group?
The what?
Like
mapping class group acts for free.
Okay.
But then the next question you ask, I don't have an answer to.
Sorry. So to get this Coulomb homology for closed null, you also need this cap and cup.
Yeah, I didn't tell you which objects with the cap and the cup.
Yeah.
I can.
Can you say from the category set?
Yeah, sure. So I was drawing this picture, and let me just tell you The basic building block is this object. Like this thing times straight lines in the file. That's the. I mean, Mina wrote this in her papers, but anyway, we prove it. We prove that this this functor intertwines this object with Webster's cap. No, that's in this paper, but I mean, how to say? It depends, like, what precisely your standards for rigor are. Like, I think Mina wrote some argument for it in her previous papers, but strictly speaking, if you want a mathematical argument, you have to look at it.
Okay, let's thank the speaker again.